Welcome to the video presentation of Group 14's convective cooling experiments for thermofluid lab. The basis of our project came from the current inadequacies of the heat transfer lab at SUNY New Paltz. The current setup is not well designed and students are not able to learn effectively due to it. This fact frustrates both professors and students alike. Our team wanted to find a way to fix this issue and make the heat transfer lab a more enjoyable and impactful learning experience for students. What we decided to do was model the cooling of a heating element from a maximum temperature at steady state back down to approaching room temperature. In order to break these models down further, we can explain Model 1 as an air-based CPU cooling tower which focuses on analyzing the effects of fan velocity on convective heat transfer. Model 2 is a water-based cooling unit which tests the effects of varying convective heat transfer coefficients on the total heat transfer rate.
In our project, we analyzed the performance of a heat sink using heat transfer principles, focusing on convection. We used the Nelson number equation. In our case, the Rayleigh number of 38,421 indicates that the flow is turbulent. Also, our Brandon number of 0.71 indicates that convective heat transfer dominates over conduction in the flow. Thus, our Nelson number of 122.8 confirms turbulent flow. Also, the total heat transfer by the heat sink equation shows how the total heat transfer depends on both the number of fins and their geometry, along with the heat transfer coefficient and the temperature difference. In this part of the project, 3 parametric studies were conducted. In study 1, the plot shows that as fan speed increases, the heat transfer coefficient also increases. In study 2, the graph shows an increase in the heat transfer coefficient leads to a higher total heat transfer. In study 3, the graph shows the combined effect of fan speed and heat transfer coefficient improves overall heat dissipation. In summary, the studies validate theoretical predictions, showing that a higher fan speed and heat transfer coefficient improve cooling and system effectiveness.
User requirements and engineering constraints. The users of these experiments should be familiar with thermodynamics and fluid dynamics, as both classes are prerequisites for thermofluids lab. It would also be useful to have experience with heat transfer, but it's not required. To obtain results from a model as near to steady state as possible, the heating element had to be placed inside a Delrin block with all but the top face insulated. To properly conduct the heat to the top of the block, a circular piece of copper and thermal paste were added between the heat sink placed on top of the convective cooler. At steady state, the current voltage, power, and temperature are unchanging, which is desired. Design iterations. Design 1 was not at steady state as the heating element was not insulated on 5 sides. Design 2 was at steady state, but the heat sinks were not permanently attached to the Delrin block and the copper plates were still square. In the final design, both models are at steady state, have circular copper plates, and the coolers are permanently mounted to their according Delrin blocks as required by our advisor.
At the core of our system is the Arduino Uno R4 Minima, which controls 3 12-volt DC fans and a 12-volt water pump, using 2 L298N dual H-bridge motor drivers. These allow for independent speed control of each output via PWM signals from the Arduino. We've integrated 2 push buttons to let the user toggle the fan group and a 16x4 I2C LCD display that provides real-time system feedback, showing which devices are active and how the system is responding to the user input, changing the fan speed. Power for the fans and pump is supplied externally to isolate it from the microcontroller, while all logic and control signals come directly from the Arduino. Now I'll pass it over to my teammate Roberto, who will demonstrate the working system in action.
We have 2 modules here. One is convective airflow, the other is convective liquid flow. We have 8 thermocouples set up, 2 of them reading ambient temperatures. Channel 1, channel on both is the ambient temperature. Channel 2 are the temperatures on the actual copper plates. From that, we can see how the heat will change when we turn this on. Now we're at case 50%. 75, we're just changing the fan speeds, and 100.